Hi students, Kushi sir again back. I'm going to discuss something on center of mass. Okay, as you see, I have drawn a situation. The diagram I'm drawing here. There is a plank lying on a rough surface. Mass of the plank is m2, and there is a person standing at one end of the plank whose mass is m1. Length of the plank is L. If the man starts walking because there is friction between plank and the man's feet, so man can walk on the plank. And there is also friction between plank and the rough surface, which I have written as F is kV with a minus sign. There is a friction force between, it's possible the surface can apply a friction force which is proportional to the velocity of the plank in opposite direction. F is equal to kV with a minus sign, where v is the velocity of the plank with respect to the surface. So there is also friction between man's feet and plank's top surface so that man can walk. Now the man walks to the other end. Can you tell me how much distance the plank will move on this rough surface? Had it been a smooth surface, no friction, this question could be very easily solved. And all of you might have done this. This is basically a problem based on conservation of linear momentum. Since if there is no friction, remember, please listen very carefully. If there is no friction between the surface and the plank, means the surface is frictionless, then on the system of plank and man, there is no external horizontal force. Okay? If there is no net external force on a system of particles, then the acceleration of center of mass should be zero. This means the velocity of the center of mass must remain constant. Initially, both of them are lying at rest. So initially, there is no motion of center of mass. So in this case, even if the man starts walking, the plank should move in such a manner that velocity of center of mass must not change from zero value. So center of mass position remains unchanged. Taking this into consideration, we can find out as the man travels a distance L relative to the plank, what is the absolute displacements of the man and plank with respect to ground, means absolutely with respect to that rough surface or ground. Okay, that is very simple. As you all know, this, I'm drawing it again. I'm drawing the diagram. Suppose this is frictionless and there is a plank here, and as the I draw my y-axis here, and call this as my y, call this as my x, and a person is here. M1, M2, then this is center of mass of the plant, this is center of mass of the man, this is x1, this is x2, then xCl of the system is, this is M1 x1, M2 x2 by M1 plus M2. As I told you, this cannot change, is constant if F net external is 0. So delta XC is 0, implies M1 delta X1 plus M2 delta X2 is 0. This is the equation 1 from conservation of momentum. And as you know, delta X1 minus delta X2 is delta X1 to the relative displacement of 1 with respect to 2. That is definition of relative concept. That is definition from the relative concept. So solving this 1 and 2, we get very simple. Solving equation 1 and equation 2, we get what we get? Very simple. You get delta X1 is M2 by M1 plus M2 delta X12 delta X2 is minus of M1 by M1 plus M2 delta X12. This is what we will get, and you all of you must be knowing this. And this delta X2 means that is delta X1 magnitude will be M2L by M1 plus M2, because L is the relative total displacement. Similarly, delta X2 will be, magnitude will be M1 L by M1 plus M2. All of you know this. Actually, I hope you know this, because there is no net external horizontal force in that horizontal direction. I can go for the conservation of linear momentum. Is it okay? Okay, nice. So now we'll go for our problem which we have given. What is our problem? Let us see. Is a rough surface. If there is a rough surface here, it cannot we cannot conserve the linear momentum, because there is an external force will be there throughout the motion. So let me draw the diagram. You might be thinking it's very complicated. Just see this. Just I draw this. Let us come to our situation. Quickly we draw this again. we draw this situation. As the man moves with a speed v, let's say this moves with a speed capital V. This is M1, this is M2. Is it okay? So, and the friction force will act on this, call it F minus K capital V. So, let's see, initial momentum before the start of walking, initial momentum of this system. System here is considered two bodies, man and the plant, was 0. As the man stops at the other end, that time what must have happened? The plant might be moving, but finally the friction force will bring it to 0 velocity. So both of them will stop. The plant also stops either same time or after some time. Stops at the plant also stops maybe after some time or simultaneously. It depends on what is the friction force acting and what is how the man is really stopping. All depends on that. That depends on the detail of the motion. But anyway, we know that the the plant has to stop. So this means final momentum Pf of the system is also initial momentum of the system. I call this, let us say, let me slightly erase it and write it again. Pi, we call this. So what is the change in momentum finally? Are you convinced that the plant has to stop? Because friction is there. It has to stop. Delta P bar is 0, Pf minus Pi. That means what we see this from this part, we understand that. That means if delta P0 means what is the net external impulse? Must be Zero. Because net external impulse is only change of momentum. But net external impulse, I write here. But net external impulse in x direction, in horizontal direction, is due to friction force between the plant and the surface, plant and the ground surface. Okay. So if that is the case, so that implies J is impulse net external is F dt from t is equal to 0 to some t. T is the time of motion being stopped. Final time the motion stops. So that is equal to minus k v dt so that is minus k. Vdt is what? Vdt is the velocity of the plant with respect to what? Velocity of the plant with respect to ground. Okay. So what will happen in that case? Zero to t dx summation will be delta x. Okay. So this is what we observe. Very simple concept. So J net external is this much. And J net external is also 0. J net external is 0 from here. Call it equation some 1. Now call this equation 2. Okay. So equating equation 1 and 2. What we get? Delta x 0. I think it's very surprising result. Very much surprising result. The Planck, the final position, this final position of the Planck has not changed from the initial position. Has not changed from the initial position. That means Planck might have been moving during the motion of the person, but finally it might have gone back, then come back like this. Understood this? Because the friction force must have changed direction. Why do I say this? That friction force must have changed direction. F delta T, just see. F delta T, F J net external is F dt integral. This is F delta T, which is zero. Okay? Because J net external F delta T is 0. I'm writing it here. Note. F dt 0 to t, I can write this if average symbol into delta t is the delta t. I call this as I think we call this as t is 0. So this implies since t is not 0, so the friction force average, friction force? The friction force which offered by the ground to the on the plant, that average is 0. That means sometimes it's acting backward, sometimes acting forward. Initially is acting forward direction because man is pushing the plant with his feet. So are moving forward, then the plant has to move back. So friction force will act forward. When man stops his motion, he tries to push the plant in forward direction. So the friction force, so plant will have a tendency to move forward. So friction force will act backward. So this must have happened. Otherwise, you see how to explain this. Average friction force while from the ground is definitely 0. That is sometimes is acting forward, then while stopping it must be acting backward. It depends upon the way the man is moving. But whatever way the man might be moving, suppose it jumps from one into other also. If it has this shifting of the plant will not take place finally. Because as I told you, I never mentioned which way man is moving. Is walking, jumping, running, how he's stopping. There may be some kind of rod on the plant, he can hold it suddenly. But irrespective of all that, irrespective of the which way the man is moving, which manner the man is moving, the plant is not changing position ultimately. If you say friction force is some other nature like constant friction force, or it may be proportional to square of the speed, then yes, depending on the value of friction, the plant final position may be different from its initial position. But for this specific case of when the friction force is proportional to velocity of the plant with respect to the floor with a minus sign, then the plant simply cannot change the position. Am I clear? Is it interesting or not? So finally, the man will simply go to the other end, and finally the plant will remain there only. So center of mass must have moved, and you must be wondering that this is so different from the frictionless situation. In that case, the plant must move back in inverse ratio of their masses. Man and plant's displacement will be in inverse ratio of their masses if the friction is not there. And also the initial momentum 0 in that case. But here it is slightly different. So I think all of you must have understood this and enjoyed this observation, and there may be some doubts in your mind, you can contact. I'll be coming time to time. You can, I've given my number, you can contact me. I think I have given in the top. Yes, Lakshmi Narayan Drushti, senior faculty, IIT Physics, BTech, IIT Kharagpur, phone number given. So this is a typical case of motion of center of mass. Not the most difficult one, but definitely interesting. Okay. If somebody, if many questions can be framed from this in single objective, a single choice, multiple correct option, I can make various questions on this, which will be new to you. Okay. So we'll meet again. Thank you for today.